What speed in knots must you cruise at? Requirements then for any glider, so we'll say a discus, and we want to achieve 300 kilometers at an average speed of 100 kilometers per hour. So in other words, take 3 hours. To achieve 100 kilometers per hour on a task, what cruise speed must you fly if you never stop for lift? Well, it's 54 knots. Dolphin. Who dolphins now? If you slow down below 54 knots, then you must subsequently fly significantly faster. We need about 30,000 feet to fly this task. Of course, the first 3,000 feet is free, so we need to climb 27,000 feet. If we climb an average of 5 knots, then to catch up on the speed that we've lost, the time that we've lost, we've got to cruise at 77 knots. Of course, in the UK, we always climb at 5 knots, don't we? If we were to climb at 4.5 knots, then the average speed must be 81 knots. And of course, if we climb even slower, then we must maintain 86.4 knots as an average speed on every glide to do 100 kilometers per hour in our task. So 100 miles an hour. Poor thermaling in respect of thermal strength then. If we look at the time taken to climb 3,000 feet, at 1 knot it takes 30 minutes, at 2 knots 15 minutes, and so on. If, however, we don't achieve that rate of climb because we're not very good at thermaling, if we just lose half a knot, then my 1 knot thermal becomes half a knot. It takes 60 minutes to climb just 3,000 feet. On the other hand, if we're at 5 or 6 knots in our climb and we lose half a knot, then our losses are very small. So whenever thermals are weak, if we can't thermal very well, then we get big or significant losses in time taken to get around in any task. And of course, time and the weather window is what limits our ability to go anywhere. The weather briefing then. First, how to make the simple briefing from first principles. Competitions are probably the worst in terms of weather briefings. You're inundated by a mass of complicated information, charts and best guesses from various people. It's easier than you think. Where's the weather we want? Well, if the sky is calm and blue, hot sunny days, very stable, well, we know they're rubbish. Some cumulus, fair weather cumulus, is always a good sign. Of course, great instability, i.e. mass instability, that we feel and experience when we get fronts going through, are no good at all. Some years ago, this graph was published in Sailplane and Gliding. It indicates how strong we anticipate thermals will be. This graph offers a guide to the ascent of buoyant air, therefore minus the sink rate of the glider, depending on the angle of bank and water ballast used. Average lift depends on the temperature and humidity of the thermal and the trigger action, and the variation of temperature and humidity of the air it is climbing through. A greater amount of cloud means shadow, and a greater amount of heat transferred into the evaporation of water. This in turn gives a greater amount of sink generated by the evaporation of clouds, generating column thermals. On this, no account is made for temperature, pressure, humidity, visibility, dimming, variations of humidity with height, wind, or depth of the cumulus. This symbol, the yellow egg, indicates achieved climb strengths calculated from basic principles, which I'll teach you a little later. Inversions. An inversion separates two different air masses vertically. The different properties of these two air masses, temperature distribution and relative humidity, makes a considerable difference to the way the sky works for us as glider pilots. Therefore, note the 2,000 and 5,000 foot wind direction, strengths and temperatures. If available, note the relative humidity. If the temperature on the ground is 20 degrees, what is the temperature at 5,000 feet? Of course, you'll have this idea that the temperature will cool at 3 degrees 1,000 feet. And so you may consider that the temperature at 5,000 will be 5 degrees. Actually, you don't know what temperature it will be at 5,000 feet. It can be anything it wants to be. But what we do know, if air is rising, it will cool at 3 degrees per 1,000 feet. So any instability generated at ground level, if it rises 1,000 feet, it will cool to 17. In this case, it cools to 14 at 2,000, 11 at 3, 8 at 4, and 5 at 5. Are all thermals the same? How do they vary? Size. Do you vary the angle bank or always find 45 degrees is an excellent angular bank to stay chord, whether the thermal is quite gentle or quite strong? Why is a thermal stronger and how is it different? How does its shape differ? Well, we find stronger thermals are deeper. They're still the same width though. How easy are they to core? Some seem easy, some are more difficult. We're forever chasing it. Buoyancy is made up of both temperature differentials and humidity differentials. Thermals. Dry thermals tend to be ragged and rough. They're difficult to stay centered on and are easily broken as soon as the temperature parity is approached. Buoyancy can be reduced or lost by conduction. Therefore, the thermal is unstable. Such thermals are generated by solar farms. Humals. Buoyancy is driven by humidity differentials, tend to be smoother and easy to center and climb in. They're very stable. Fuselage lift is more easily exploited. So showery days, middle air to instability, climbing over pig farms or worked fields, and woodlands late in the afternoon. And thermids. Buoyancy are made up of temperature differentials and humidity differentials. Both drive up to the inversion, with humidity continuing above the inversion and possibly cool enough to generate a cloud base. Here we have, on the 8th of July, a meteorological cross-section. Vertically we have height, horizontally we have time. And this is relative humidity air variations do occur during the day. In this particular example, it just gives it at the beginning of the day and the end of the day, but it can vary considerably during the day. And here we have relatively dry air, and it is a bubble day. The wind then is westerly at 10,000 feet, 27020. The temperature at that height is 3 degrees. When we look at the 5 and 2,000 foot winds, we can see that at 5,000 feet it's 29015, the temperature is +8. The 2,000 foot wind though is 33015, and the temperature is initially 9 degrees, and that air is warming to 13 degrees. So if we look at the instability between 2,000 and 5,000 feet, the air at 2,000 feet is 9 degrees. It goes up 3,000 feet where the temperature drop is only 1 degree, so it is relatively stable. However, later in the day, it's 13 degrees. So now we've got 5 degrees in 3,000 feet, and there's again a little bit of increased instability in that air mass, primarily with a bit of humidity. We have bubble days. In other words, all the thermals are hot air rising from the ground. Later on, we can see at 3 o'clock in the afternoon, the surface air temperature is 23, and then it starts to cool off during the later part of the afternoon to 21. So this is the 8th of July. Humidity then, 85%, quite moist at the bottom there, to 60% at 5,000 feet. Later on in the day, because the air has warmed up, it's got less humidity in it, so it's dry air going into humid air. Humidity mass decreases with height for the same percentage relative humidity. Here we've got some northerly dry air. Notice here the surface wind is very steady. There's no forecast gusts, which again means that sinking air is not coming down, hitting the ground and giving us a blustery day. So again, it's another indication that the day is going to be a bubble day. We now look at the very next day, 9th of July. So effectively, the sun is having exactly the same effect in heating the ground and heating the air. However, we've got a more westerly wind here, and we've got a lot of middle airspace instability. So here, the temperature at 2,000 feet is 14 degrees, considerably warmer in the morning. Wind at height, 26020, the temperature's +2. And here we can see 14 to 9 degrees, making it already unstable, and it's becoming 17 to 9, so that's 8 degrees in 3,000 feet, and that's giving considerable instability. And this generates column thermals. We can see the temperature is warmer later in the day at 25 and 24 when we get to 6 o'clock in the evening. So 3 degrees warmer in the day, later in the day than the day before. More humidity in the atmosphere, 90% at the beginning of the day, going to 95%. this here low humidity is because the temperature is so much warmer than it was the previous day. Here in the forecast we've got not a steady wind but a wind with gusts, and again there's the indication that we're going to get column thermals, and we can actually connect underneath clouds quite low and climb away in quite strong thermals. In other words, the cold air, which is made cold by the evaporating cloud, cascades all the way down, falls all the way down to the ground, hits the ground, and that's where our gust comes from. Of course, the stronger the gust, the stronger the thermals that are generating it. So today we have 4 knot thermals with a surface gust of 5 knots. Having a look at another day then, this time not in summer but in almost midwinter, 16th of February. We can see the wind is steady and quite a lot of stability is indicated, but within those bands there must be some level of instability because we have cumulus developed. However, they're indicating 1 knot thermals, and sadly 1 knot thermals in reality don't exist. During the day then, the air mass becomes layered. And here we can see two separate air masses. The mountain range has made a barrier to the air mass to the north. So the north is much more moist, colder air, and the cloud tops, in fact, are just high enough to start pouring cold air over the ridgeline. So each layer can have blocks with different levels of humidity. So here we have a very light surface wind, 300 feet to 500 feet and below. And within that, there'll be lumps of humidity, differing lumps of humidity, which will give different blocks of air with different properties. Overnight, humidity is adjusted overnight within the lowest level. So we get an overnight inversion, beneath which we're adding humidity through power stations, vehicles, breathing, and so on. As the day warms up, then this humidity is allowed to escape into the lower level. And here we end up with blocks of air with varying degrees of instability. Some areas are cloudy, some areas are clear. Of course, at the highest level, we have contrails. Those also have a significant effect on the instability of the atmosphere. The air mass becomes layered, containing different winds, and the wind brings the weather. Dew point, i.e. cloud base, can occur within or on the boundaries of the blocks. Of course, fronts change the upper air blocks. Down here, Reynolds number is significant for generating turbulence, which helps evaporation and the conduction and transfer of heat from the ground to the air. So, bottom 10 to 300 feet, Reynolds number is very applicable. As the day warms, the surface wind will increase and the lowest inversion breaks. Surface wind will increase. Of course, in our basic lessons on meteorology, we're told or you will have been told that temperature decreases with height. Well, not always. And here we can see the surface level is a little less than freezing. At 2,000 feet it's +3, at 5,000 feet it's +2. And yet we can see the red lines, the red dashed lines, indicate the freezing levels. And we can see 3 freezing levels here, within which there's a positive temperature of air. So there's little layers of instability, which is where the cumulus is being formed. So these inversions here are like immiscible fluids. There's no mixing between the layers. Here we've got middle airspace instability, cumulus 8,000 to 11,000 feet. Here's another cross-section from the UK Met Office. The winds then, up on the left here, so 060, 10 knots, and it's saying the temperature is +8. It's veering a little bit to 5,000 feet, but then it's backing again at 10,000 feet. Again, you've been taught that generally, on average, winds veer and increase with height. And we can see that that's not always true. Temperature with height, and what are the thermal strengths? So, in this case, it's indicating 2 and 4 and even 5 knot thermals. So we've got this instability at height, which is very strong. Again, it's a bubble day because you can see the surface wind. There's no variation in the surface wind whatsoever. So this is a middle airspace day for us. To get low would really mean that you're probably going to land. Humidity with height, the numbers are given there. And the freezing level, well, it's not actually indicated on this slide. Here we have another cross section then. We can see that a front is coming in and the wind and temperature is going to change at 2,000 feet during the day. So starts off with a northerly at 2,000 feet, 36025, and it is backing and reducing during the day. Clean air with active cumulus and water temperature below freezing. And whilst we often talk about water freezing at 0 degrees centigrade, actually pure water will freeze at about -12. Of course, what I've been showing you is UK official meta-analysis for gliding and soaring. And in the UK, this forecasting I would have to consider is poor. The thing is, we don't pay the Met Office enough money to have a more accurate forecast. So here's a French forecast for gliding. On the left, it has the air blocks for the areas, and those areas are bounded by high ridge lines effectively, so it means that that block of air and its properties will stay within that local area. To the right is a cross section, a little bit similar to the cross sections we've been seeing. So that area in red, the properties of that area are indicated in the right hand side of the slide. Zooming in then, we'll have a look at it. Firstly, 2-hourly blocks of time marked along the bottom. Temperature and dew point every hour. Heights on the left are in thousands of meters. Wind strength and direction is about every 1,000 feet. and there's a thermal decode on the right. So 3 meters, about 6 knots to almost 9,000 feet in this slide. And here we can see we have an operating band. As we get too low, or as we get lower, we can see thermal strength is going to reduce below about 12 or 1300 meters. This green line shows the distance a standard class glider might achieve if it's only using thermals. Here's the freezing level, and this other green line here is the distance a standard class glider might achieve if you only use wave. In this one we have the area to the northeast of the previous slide. The red blocks are showing inversions. Weather forecasting. RASP was 12 kilometer bitmap and it's now better. 4 kilometer bitmap on the day, and each property is calculated and presented separately. In fact, on occasion it's now presenting 2 kilometer bitmaps. Is there a better model? Well, for some areas, forecast24.com is produced by a Raspberry farmer in Slovenia using the same raw data that RASP uses. Comes down to 1 kilometer square bitmaps and combines insolation, winds with altitude, subsequent convergence, temperature, dew point and topography. But in fairness, it's not that good for the UK, and not because of a failing of the system, but the uniqueness and difficulty of actually forecasting in the UK, which I'll cover in a moment. So what about the UK? Well, we like things for free. So here we have, from the Met Office, a forecast with quite a lot of information, some of which is useful to us. Firstly, the yellow warnings and so on, well, we're not very interested in that. The feel like temperature, we're not interested in that. The UV index, we're not interested in that. So here we have time along the top, anticipated cloud, temperature, winds, visibility and humidity. Humidity often relates to visibility. There can be big variations during the day, and as a forecast, well, this is free and it's better than nothing. Visibility, poor, medium, very poor, and so on. Humidity. On the surface, tells us there. Very good and good. Later in the day. In fact, in the evening. At cloud base, well, we can tell our humidity by the amount of cloud that's up there. Note the surface wind. It's unstable all day and even into the night when there's no sun. There is no diurnal variation because we can see there's quite a lot of fluctuation in the wind, quite a lot of gust factor. A good day forecast. Look for air mass. A period of dry weather, or a cold front has passed through overnight. It might even have rained overnight. The air is unstable over a large area, producing consistent structure to the sky. The wind direction has some north in it, usually from the northwest. More northerly has less effective contrails, giving better visibility and a stronger sun. So pure northerly is just wonderful. And here we can see the effect of contrails. So the Met Man can forecast the height at which contrails will be formed, but he has no idea how many airliners are going to fly in that height band and therefore leave a lot of contrails around. So our otherwise beautiful day is no longer beautiful. If you remember when the Icelandic volcano grounded European airspace for about 2 weeks, the sky was unbelievably blue, and it was a great couple of weeks for gliding. Of course, as I said, he can predict at what height the contrails will develop, but he has no idea how many will be generated. Therefore, it's unpredictable. I can see the airliners here charging off through Prestwick and out to the west. Contrails in the northwesterly will cover the country. So, basics then, a good day forecast. Look for temperature difference and calculate cloud base. The bigger the difference between the minimum overnight temperature and the maximum midday temperatures, the higher the cloud base, or the maximum height of the inversion. Cloud base is the above difference divided by 2.5. In other words, the average environmental lapse rate times 1,000. So, if the minimum overnight is 10 degrees and there's a bit of dew on the grass, so that is dew point, and the max forecast is 20 degrees, that makes a difference of 10 degrees between min and max temperature forecast on the day. Divide this by 2.5 times 1,000, so the cloud base is 4,000 feet. Or if you wish, for each 1 degree temperature difference, cloud base is moved by 400 feet. Meaningful for cross-country cloud base, then cloud base we need at about 3,500 feet. To calculate thermal strength then, because the sky is physics, it's cloud base, which is 4,000 feet. So 4 times 1.2 is 4.8, minus 1 for a notional fall of the glider is 3.8. So the thermal strength will be 3.8 knots. Cloud cover and humidity. Well, few is good. Scattered can have 50% cloud cover, and that's just looking at it vertically. Of course, clouds have got vertical extent, the sun hits it at an angle, so we could have 60 or 70% cloud shadow on the ground. So scattered is not really a good sky for us. When to get airborne and where to go cross-country? Well, to make the most of any day when endurance is required, so 5 hours, or a big task, then it's best to get airborne just after the day has started to develop. It should then only get better, or easier, depending on your point of view. Wait until the short grass is dry, because then you've got both temperature and humidity driving the sky. After the surface wind has increased and veered, in other words, we're starting to get a blustery wind, which means the column thermals are working and the sink from the evaporated cloud is working all the way from the tops of the clouds all the way down to the surface. Any direct line down the middle of the country. a good day forecast. Look for wind. But what wind? Well, Reynolds number does apply to us. So when the wind is over 8 knots, we end up with a turbulent flow over the surface, and that increases the amount of evaporation and transfer of heat. And if you think about it for a moment, consider a hairdryer with no fan. Yes, it gets very hot, but there is no warm air generated, or very little warm air generated by the hairdryer. So less than 8 knots produces good enough thermals, but they tend to be a long way apart. The sky is erratic. The mechanical mixing of the air does not happen. There's poor conduction. The sky is often blue, and sync dominates large areas of the sky. It can be difficult, and of course sea breezes can get inland a long way and kill huge areas. Greater than 15 knot surface wind gives slightly tighter thermals with stronger triggers, and generally more difficult into wind unless you've got streeting, and it's certainly difficult doing crosswind lengths. It can also generate a wave influence which interacts and interferes with the thermal structure. So 8 to 15 knots is ideal for cross-country cruising. There's also a weather app for smartphones, Windy, which is free and is very popular. Where does the wind come from, though? And where does the surface wind come from? Well, the wind is generated from the flows from high pressures to low pressures. The wind tries to go in a straight line, but can't because of Coriolis. So the wind goes tangential to the highs and lows. And of course this particular forecast is not very good for gliding in the UK. Simple air plot, diurnal variation then. Here we have 20 knots generated by the gradient wind. We're going to say that the temperature is 10 degrees at, say, 2,000 feet, and 8 degrees lower down because of cooling. And so we end up with an inversion. So there's no mixing vertically of the two lumps of air. Inversion is formed, and down here in this lowest level, humidity increases and remains trapped. Humans breathing, animals breathing, transpiration, various exhausts, and of course evaporation. The thing is that the objects on the ground drag the surface wind to almost nothing. So it could be 5 knots or calm. In the morning, sun comes up and starts warming up this lower air mass. We get a little bit of instability, and the inversion starts to break. As warm air goes up and humid air goes up, cooler dry air comes down. But that air was moving along at 20 knots, and it whips up the surface wind. It accelerates the surface air, and it becomes windier and blustery. Might go to 15 knots. Quite often it gets to about 3/4 of the 2,000 foot wind. Of course, at night, when it all cools down again, the surface wind may well die away. What influence thermals? The interaction of the following. and note that not all thermals are generated from the hot ground. The instability or potential instability of the atmosphere. Ground dampness. Humidity and relative humidity. The wind. Convergence. Troughs. The sun. The ground ability to absorb and heat the air, i.e. dark and dry areas. The angle of sun to the ground. Thermal contrast of adjoining surfaces. Cloud shadow, including the amount. Clouds evaporating. So here's a little revision then towards self-tasking from basic principles. Calculate the cloud base and thermal strength, and you can decide where to go simply by looking at a newspaper. So here we have our minimum temperature and our maximum temperature. We know its cloud base is produced by the temperature difference at 400 feet per 1 degree. So we can say there that the cloud base is 4,000 feet at home. As we look around, we'll see cloud bases will vary quite significantly in areas. Sometimes over 5,000 feet, sometimes only 3,000 feet. Then think wind, landable areas, unlandable areas, airspace. Summary then. Sync dominates the thermic sky. Relative humidity is as important as temperature differences. The sky may be layered. Critical wind strengths, cloud amounts, temperature highs and lows for basic cloud base and thermal strengths.